Hello and welcome to another Arlington High School Math 4 Honors lesson. I'm Kirk Weiler, and today we're going to be doing Unit number 7, Lesson number 7 on our third day of one-dimensional motion, Motion Day 3. So we're going to do only one more lesson. That'll be the next one on modeling the motion of a rocket, and then we're going to be moving on to other topics like vectors. But for now, we're going to look at one-dimensional motion in just a single context. We're going to look at constant acceleration. So those of you that have had physics before have seen this before, but maybe not with calculus thrown in. So there's a lot of situations in physics where the acceleration on an object is not a function of time, where it's simply constant, right? A good example of that would be an object that's just falling, all right? So if we had like a basketball that dropped, all right, not the bouncing, although that's still really only acting under the constant acceleration due to gravity, although once it starts bouncing, there's other things happening. But really, just in general, anytime you have a constant force, so if we had like some block, let's say, that we were pulling on with a constant force, then what would happen is that that block would experience a constant acceleration. Now, throughout what we're going to do today, there's really just two things that you have to keep in mind, right? And these are the keys to the problem. You have to remember that acceleration is the derivative of velocity with respect to time. And velocity is the derivative of position, either x if we're measuring horizontal or y if we're measuring vertical. Okay? So all we're going to be dealing with today are acceleration functions that are constant. Okay? So let's take a look at the first problem. An object moves vertically with a constant acceleration of -6 meters per second, or meters per second squared. Okay? So it's a constant acceleration, -6 meters per second. Its velocity at t equals 0, so its initial velocity, as physicists call it, is 8 meters per second, and its initial position is 3 meters. What we want to do is determine equations for the object's velocity and for the object's position. Now, what we know is that the acceleration is -6. And we also know that that is the derivative, I'll call it v prime, of the velocity. So the question is, what is the velocity's formula? I'd like you to pause this video for a minute and think if you can write down a function. Now remember, the independent variable is t, not x. Watch out for that. See if you can write down a formula for the velocity. All right. Well, I'm hopeful that you at least wrote this down, -6t. Okay? Now, the discussion we're going to have next is extremely important. Certainly, if the velocity was -6 times t, then the acceleration would be -6, right? But it would also be true if I had -6t plus 7. It would also be true if I had -6t minus 8. All of these would give me the correct derivative. In fact, when we do this process, when we go backwards, right, we're really going backwards, what we're finding is what is known as an antiderivative. And every function has an infinite number of antiderivatives, an infinite number. And that's because of that constant that's tagged on at the end. So what we do is we don't say that it's -6t. What we do is we say that it's -6t plus a constant. I'm going to call it C1 because there's going to be another constant that's going to come up in this problem. And then we have to solve for this. We have to figure this out. Find this. Now we're going to do that by simply using this fact. At t equals 0, the velocity is 8 meters per second. So in other words, v of 0 is 8. Right? So I'm going to put 8 in. I'm going to put 0 in for t, and no great surprise, I find that C1 is 8. So now I can actually give my velocity formula, -6t plus 8, right? And notice it really satisfies two things. The first thing it satisfies is the fact that its derivative is -6. But the second thing that it also satisfies is the fact that its initial value is 8. Right? These two things have to be true about this formula. All right, let's find the position formula. We'll do it up here. Now, in this case, we're modeling the vertical position, right, y. So what do we know? Well, we know dy dt, or y prime, either way, is equal to the velocity, which is negative 6t plus 8. All right, so we're going to find the antiderivative of velocity to give us position. Okay, now think about this. What would we have to have a derivative of negative 6t? Pause the video if you need to. Hopefully, everyone found that they would have negative 3t squared, right? Think about bring the 2 down, negative 6, etc. Now to take our derivative and get 8, we'd have to have 8t. And we'd have to have another constant thrown on. Excuse me. To figure out our second constant, we're going to use this. We're going to use the fact that at t equals 0, y is 3. So I'll get 3 equals negative 3 times 0 squared plus 8 times 0 plus c2. All these go away, and c2 ends up being 3. Please don't jump to unwarranted conclusions like, oh, that's going to always be c1, that's always going to be c2. Maybe if we're dealing with polynomials, but not otherwise. All right, and there's our position function. So what we do is we go backwards. Sorry about that line. We go backwards through our derivatives by finding antiderivatives. That's kind of a cool term, isn't it? All the antiderivatives we're going to be working with today are going to be power law type of antiderivatives, but you could have almost any kind. A big focus on your calculus studies for next year will be finding antiderivatives. But for now, we're going to clear out the text, so pause the video if you need to. Okay, here goes the text. Let's flip the page. Excellent. All right, exercise number 2. Now we're going to go more generic, and we're going to come up with one of the most famous physics formulas that almost every first-year physics student learns, but oftentimes teachers have a hard time sort of explaining where this formula comes from because the students don't have calculus. But now watch how easy it's going to be. It says, given an object is moving vertically only under the influence of gravity with a constant acceleration of g. All right, so very often physicists use g to represent the acceleration due to gravity. An initial velocity of v0, so in other words at t equals 0 we have a velocity of v sub 0, and an initial position of y sub 0. We want to find equations for velocity and position as functions of time. Okay, great. Well, what can we start off with? Well, we can start off with the fact that a of t is this constant g. Now remember, that's a constant, right? It's like our negative 6 from the last problem. It's a constant, okay? So the velocity function, right, which will be the antiderivative, will be g times t plus some constant. Right? That's it. And just think about it again. If I took the derivative of g times t, I'd have just g. If I took the derivative of c1, that would go away. Now, what's true is that v of 0 is v sub 0. And if we just kind of work that out, right, what we'll find is that c1 is v sub 0. So we get this particular function for our velocity. v of t equals g times t plus v sub 0. Okay? Now let's figure out our position formula. Now we have to do the antiderivative of this beast. Now this is going to be a little bit trickier. What would you have to take the derivative of to get g times t? Pause the video now and see if you can figure that out. All right, let's go through it. Well, you know it's going to have a t squared in it, right? But if I multiplied by t, if I had just t squared, I would have the 2 that would come down when I took the derivative. Therefore, I need to have a 1/2 sitting out front so that when I take the derivative, that 2 and that 1/2 will cancel and leave me with just a 1. We have to be careful here. To get a derivative of v sub 0, we have to have v sub 0t, and then we have to have another constant thrown on. We know that y of 0 is y sub 0, and that will eventually give us the value of c2. So y of t equals 1/2 gt squared plus v0t plus y sub 0. That is a very, very famous physics formula. Very, very famous. Very often when you're modeling a ball just dropping from a certain height, the center term will not even be there. right? All you'll have is 1/2 gt squared plus y sub 0. Okay. But let's take a look at exercise number 3. An object is fired vertically with an initial velocity of 126 meters per second from a height of 4 meters. If the acceleration due to gravity is negative 9.8 meters per second, then determine when the object reaches its highest point and the height it achieves at this point. Well, let's do the following. Let's write down our velocity and our position formulas. Now I'm not going to rederive this, I'm just going to use what I learned before. V of t equals gt plus v sub 0, so in this case the velocity function is negative 9.8 times t. What was our initial velocity? Plus 126. Now I want you to think about an object that goes up and then it comes down, right? You've looked at this a lot. One thing that you should know is that its highest point, v of t, is going to be 0. So if I want to determine when the object reaches its highest point, I'm just going to do negative 9.8 t. Whoops, that didn't work out. Negative 9.8 t plus 126, set that equal to 0, solve. It's not going to be the prettiest thing. 126 divided by 9.8. Can't do that in my head, but we're going to get something ugly, 12.857 seconds, if we take it out to that 3 decimal place accuracy. So that's when it hits its highest point. Now the question is, at what height is it at? Well, for that, we need the height formula, right? Y of t is going to be 1/2 times negative 9.8 times t squared plus 126 times t plus 4, right? So all I really need to do now is just take this and substitute it into this height equation. You know, very often physicists will clean this up, make it into negative 4.9, but whatever, it's up to you. So I'll find y of 12.857. Whoops, sorry about that. And that ends up being 814 meters. Accurate to the nearest meter. Right. We don't need it any more accurate than that. It would be a little silly. All right, so that's kind of neat. We got one of the most famous formulas in physics, that 1/2 gt squared plus v sub 0 t plus y sub 0. Then we can immediately turn around and apply it. Okay. I'm going to scrub out the text, so pause the video now if you need to. All right. Last page. The last thing that we're going to do today is look at piecewise constant acceleration. So up to this point, we had an acceleration that was always negative 9.8 or always negative 6 or whatever. But very often we have a situation where an object accelerates over a certain amount of time, reaches a certain velocity, and then stops accelerating and maintains that velocity. So an unchanged velocity would mean an acceleration of 0. So let's take a look at that situation with somebody who's running. Okay, it says a runner is racing in the 400-meter dash in an event. She starts with an initial position of 0. That's actually an initial velocity and position of 0. All right, so let's say we're saying x is position, so that's going to be 0. V is velocity, that's going to be 0 at t equals 0. Okay, her acceleration is given by this piecewise function. So let's say for the first 2 seconds, she's accelerating at 3 meters per second, and after 2 seconds, her acceleration is 0. It doesn't mean she's slowing down, folks. It actually means the velocity is not changing at all. All right, that makes sense. That's the way runners oftentimes run. Given that velocity must be a continuous function, I'll explain why that's important. Find a piecewise formula for velocity, sketch a graph of your final equation. All right, well, let's not worry about that whole continuous thing. Let's just think, right? If all we do is do antiderivatives, then our first formula would look like that, and our second formula, and this is a little tricky, would look like that. Now I want you to pause for a second and think about this. If I took the derivative of 3t plus some constant, I'd get 3. If I took the derivative of a constant, I'd get 0. All right, the question is, what are those numbers? Well, in order to get c1, right, we would have to use the fact that v of 0 is 0, right? So we'd get 0 equals 3 times 0 plus c1, and c1 would be 0. Okay. So I'm going to actually erase that now. c1 is 0. Okay. The question is, what's c2? That's where this little phrase about velocity being continuous is so very critical. So in order for velocity to be continuous, then this and this have to have the same value at the cutoff point. In other words, 3 times 2 must be c2. So c2 must be 6. In fact, I'm going to write that in here, save myself some room, and there's our velocity function. Let's graph it. This is actually kind of nice, right? So t and v. What do we know? Well, we know it's linear going through the origin, and after 2 seconds, right, it's going to hit 6, and then it looks like this, right? That's it. That's our velocity function. So our runner speeds up, right, gets up to 6 meters per second, and then levels off. That's where she stays for the rest of the race. Now it says, given that position must be continuous, find a formula for the position of the runner as a function of time and graph your final equation. All right, let's do it. So let's call it x. Piecewise formula. All right, what would the first thing be? 3/2 times t squared plus constant 1 or constant 3, however you want to think about it. Second one would be 6t plus c2. Okay, now same deal for 0 to 2 greater than 2. To figure out c1, we would use the fact that x sub 0 is 0, but that would actually result in a c1 being 0 again. So now, to figure out c2, we'll use the fact that this formula and this formula have to meet up, right? In terms of limits, it means the limit coming to 2 from the left has to be equal to the limit coming to 2 from the right. All right, but mechanically, we're just going to do this. 3/2 times 2 squared equals 6 times 2 plus c2. That's 4 times 3/2 is 6 equals 12 plus c2. And c2, is negative 6. I'm going to actually erase that and do that. All right, let's take a look at this graph. Now, I know this tends to really mess with people's heads, but this is my x, and this is t, and my cutoff is at 2. Now, what does that look like? It looks like a parabola, right, that gets up as high as 6, okay? And it looks something like this. Right. Now, we know that this one starts off at 6, but what happens is it's just linear, right? So it just sticks with a line of 6, right? If we kind of projected this backwards, we could eventually get that y-intercept of negative 6, but we're not going to worry about that. So a nice, beautiful parabola smoothly transitioning into a linear. That's almost exactly what we did when we looked at differentiable piecewise functions, right? And we made sure the derivatives matched as well as the y values. Isn't that cool, though? All right, I'll clear this text out before we finish up the problem. Okay, let's move on to the next sheet. All right, so to the nearest second, when does the runner finish the race? I mean, how good is this model? Well, in order to do this, we really need what we just found. Okay, we need that position formula. So we've got it now. Now, when does the runner finish the race? Well, the runner's going to finish the race whenever this equation is solved, right? We got to solve this. Now, you might say, well, how do I do that with a piecewise function? Pause the video now if you think that you can figure out when she finishes the race. All right, let's go through it. Of the two formulas, we should pick this one. She definitely finishes the race after 2 seconds, right? I mean, not like right after 2 seconds, but sometime after 2 seconds she finishes the race. So all I need to do is solve this. 6t minus 6 is 400. Of course, t then would be 406 divided by 6. And we would find that was 67.6 seconds. Round that up to 68. Very reasonable 400 time. All right, that's the whole deal. It's kind of neat, isn't it? Piecewise acceleration functions. We're going to work with them more in the next lesson when we model the motion of a rocket. All right, when we become rocket scientists. I love it. But pause the video now if you need to write any of that down. All right, let's finish up. Okay, well, that was our last really kind of formal lesson on one-dimensional motion. We will play around with it a little bit more next lesson when we model the motion of a rocket. But for now, I'm Kirk Weiler. This has been another Math 4 Honors Arlington High School lesson. Until next time, keep thinking and keep solving problems.